the main math that we need for this class, which is just vector relationships. And a lot of this stuff, probably all of this stuff you've seen before, but maybe not exactly thinking about the relationships in the way that I'm, presenting it here. But I would say that the main determiner of how well you do in this class is stuff that we're going to talk about in the next day or two. The people who really can wrap their heads around these vector relationships, these vector relationships are the things that just keep coming up. And if it never just comes like that to you, then it slows you down on everything else we're going to do. So even though you've seen, nothing here is going to be like, wow, I never, it's this way of thinking of these approaches is going to be really important. So even though it's largely review, take this next day or however long this takes seriously, okay? So vector review. So first of all, say we have a vector. Let's say it has a length of 1.5 and it makes an angle of 30 degrees with the horizontal. And let's say I ask you for the vector components. In your math classes where you've talked about vectors before, there's a pretty clear answer to how to do that. But I just want to remind you that that answer doesn't have a question. That question doesn't have an answer at all until you choose a coordinate system. Okay, and we're going to choose, our coordinate systems are going to rotate around a bit. You saw it, I know, in Physics 1 when you did things sliding and rolling on inclines. And I think there'll probably be times when there's no reason to use a weird coordinate system, and so I'm sort of sloppy and I just act like we know what it is. But remember that components can't be defined until you know what your coordinate system is. So not defined until you choose a coordinate system. Okay, so if you choose a coordinate system like the one we're most used to, that's x and that's y, then to figure out the components of that, put the tail of the vector at the origin, and the vector would be 1.5 times, you go, you can just go counterclockwise from the positive x-axis to the vector. So in this case, that would be 30 degrees, cosine and sine of 30 degrees. And so you get like 1.299, 0.75. But if you choose a different coordinate system, so say that I chose a coordinate system like this, where the x-axis is 30 degrees offset from the horizontal, that means the x-axis is pointing in the exact direction of the vector. And so in that case, the vector would just be equal to 1.5 in the x direction, and you wouldn't have to go in the y direction at all. And so now some calculations that are going to be important to us. First one is, well, let's do adding two vectors first. Okay, so if you are adding the vector AB to the vector CD, the fact that you have these vectors in a component form means that the coordinate system's already been defined and everything. And if you add these up, you get an x component of A plus C, a y component of B plus D. All this stuff works in 3 dimensions too. Multiplying two vectors. No, not multiplying two vectors. Multiplying a vector by a scalar. Scalar just means a number. So if you're multiplying the vector D, so the scalar D times the vector A, B, I'll do this one in 3D. The product is multiply the scalar times each one of these components. So dA for the x component, dB for the y component, dC for the z component. A lot of times we're going to want to figure out the length of a vector where we have the components. So to calculate the length of a vector, if the vector is equal to A, B, C, the length of the vector, we'll write that as an absolute value of a vector, is equal to the square root of all of this, A squared plus B squared plus C squared, all square root. That's the Pythagorean theorem. In 2D, if your vector was just AB, then the length would just be square root of A squared plus B squared. Yes?
Does that work regardless of the dimension?
Yes, but for mechanics classes, you'll never use vectors bigger than 3 dimension. Multiplying two vectors now. There are 2 ways to do this. There's only one way to multiply a vector by a scalar, but the 2 ways, what are they? Yep, dot product, cross product. The dot product, the inputs, so for both of these 2 ways, the inputs are both vectors, right? We're multiplying 2 vectors together. But for the dot product, the result is a scalar. So sometimes you see this called the scalar product. And the cross product, the output is a vector. So sometimes you see this called the vector product. Also, the dot product is sort of a measure of, among other things, it's a measure of how close to being in the same direction 2 vectors are. If 2 vectors are in the same direction, the dot product is as big as it can be. If they're in the opposite directions, it's as negative as it can be. And if it's, and you know, as it goes from 0 to 90 degrees, that value gets smaller and smaller, and that's why sometimes you see that called the inner product. It's like a measure of how close to in the same direction they are. And the cross product is the opposite. If you think about what are some things that you use the cross product for, like calculating moments, you know, to get a big moment from a certain force at a certain location, you want the force to be perpendicular to the line between the about point and so the cross product is the biggest when the two things are perpendicular, and that's why this is sometimes called the outer product. Okay, the dot product first. If you're taking the dot product between a vector A, B, C, and a vector D, E, F, the answer is the product of the x components plus the product of y components plus the product of the z components. So both of the inputs are vectors. The answer you get out is a scalar. That's just a single number. And on most TI calculators, once you define the vector, so let's say the vector A, you've put in the vector 1, 2, 3. And there's a couple of ways to do that. On TI-89s, you can write that as square brackets 1, 2, 3. On TI-84s, you can do that as square bracket with a square. So, and the semicolons go to a new row. So what this is saying is that's a column matrix. On TI-84s, the notation has to be a little bit different. You do it as square bracket and then a square bracket for each row. So 1, 2, 3. On TI-83s and 86s, I believe, whoops, there's a square bracket for the whole thing. You have to go to the matrix thing and go to edit, and so I'll just write it as matrix edit. And let's say that the variable b has the vector in it 4, 5, 6. That makes sense. You can use that same format for it. Then the command you use is just dot key with the arguments A, B. And the way you get to that function is go to catalog, or I guess you can find this on some calculators in catalog. In some you can find it under matrix and then math. So see if you can figure out how to enter this in your calculator, and if you can't, let's talk about it after class or office hours or something. You really want to figure out how to do this in your calculator because it'll save you 1,000,000 hours of dumb, pointless math. Okay. Notice this important thing about the dot product. The order of the of the arguments doesn't matter. So A dot B is equal to B dot A. You enter these into your calculator, and you do dot product of A comma B, and then you do dot product of B comma A, you'll get the same thing. And by the way, if you want to use this as a check to see if it gives you the right answer, the answer for that should be 32. Make this, so notice, let's make this the first one. And there's one more thing I want you to keep in mind about the dot product. And that is that the dot product of two perpendicular vectors is 0. Any questions about dot product? And then the second type of matrix multiplication is the cross product. The definition of the cross product, so if you have the vector ABC crossed with the vector DEF, remember this is a vector product, so the output has to be a vector. The x component of the output vector is BF minus CE. The y component is the negative quantity AF minus CD. And the z component is AE minus BD. On TI calculators, if you put the vector, oh, this is a lazy one, 1, 0, 0 into A, and the vector 0, 1, 0 into B, then to do the cross product of those two, the function is cross P of the vectors A and B. And that'll give you a vector back 0, 0, 1. The cross product is useful for making sure that, so remember there are a lot of times where we're going to have to choose our own coordinate systems. When you choose a coordinate system, it has to be a right-handed coordinate system for all these math rules to work. And the easiest way to figure out if you have a right-handed coordinate system is to use the cross product requirements. And the requirements are that the x-axis crossed with the y-axis is equal to the z-axis. So I'll write that as I cross j is equal to k. I'll skip ahead to C. We'll come back to B in a second. The x-axis crossed with the y-axis crossed with the z-axis, so j cross k is equal to the x-axis. Okay, so notice those are, if you just sort of do these in order, this is what you would expect. The second one, if you take the x-axis, I, and cross it with the z-axis, k, you get the negative j-axis. Those are the requirements for a right-handed coordinate system. And notice a trend starting to develop here. Look at this frickin' y-axis. Here, here. The y-axis in any kind of vector rule, it's like it's sort of trying to follow the rules, but it always just has to be a little different. It's got to get its negative in there somewhere. I don't know what it is about the y-axis. You know, like, did you have any kids like in your high school who like spent the summer in England and then like walked with a like walking umbrella for the rest of high school or something? Like, just like something, they just thought they were just a little too good to act like everyone else or whatever. That's the y-axis. Or like talked with a British accent the rest of high school. That's the y-axis. Okay, so cross product. Here are the things to notice about the cross product. First, the cross product of two parallel vectors is 0. The output is always a vector, so it's a 0 vector. So that's true if the vectors are in the same direction or if they're in the opposite direction. And then second, with the dot product, remember the order didn't matter. With cross product, the order does matter. And if you take the vector A cross B and the vector B cross A, they're opposites of each other. So A cross B is equal to negative B cross A. Any questions about the cross product? The next thing we're going to use all the time is a vector from one point to another point. So let's say a vector from point A to point B. And another way that I'll say this sometimes is, you know, don't get mixed up by the order that I write these down in. I'll also sometimes write this as 2B from A. But we're talking about the point B being the destination and the point A being the starting point. And also when I talk about points, I'm talking about the coordinates of that point. So what's the difference between coordinates and vectors? Really nothing. You can think of the coordinates are a position vector. They're a vector that goes from the origin to the location of the object. So coordinates are really position vectors. And so you can do vector operations with coordinates the same way you can with other vectors. And so there are sort of two ways to think about this, and each is useful at certain times. Two ways to approach this. The first one is if you know the coordinates of A and B, then you just take the destination point, treat it as a vector, its coordinates, minus the starting point, treat it as a vector. So this is the destination. This is the starting point. But there are other times when, okay, so when would you use this? You'd use this. This is the easiest way if you already have the coordinates for A and B. Sometimes you do. But sometimes you don't already have the coordinates for everything in whatever your chosen coordinate system is, and you'd rather not have to go through the process of figuring out the coordinates for every point. Then what you do is, if you don't have the coordinates for A and B, then it doesn't matter if your true origin for the problem is at the point A. Just imagine that the origin is at A. That point A is the starting point. And with the origin imagined at A, just calculate the coordinates of B. Based on that assumption, based on the origin at A. Okay, so B is the destination. Okay, let me do an example. So let's say that's a wall and we have a cantilever beam at an angle. where this angle is 30 degrees. The length of this beam is 0.5 meters. Let's say that this is the point A, and this is the point B. And in the standard coordinate system that we're used to, the vector to B from A. Well, we have these two different approaches. Well, in this case, I mean, I didn't even give you what the origin is. So, I mean, you could choose an origin and then calculate coordinates based on that and everything. But let's just start by saying we'll put the origin. Okay, so this is sort of that second method. We'll put our origin at A. Move it down a little. So here's the point A. Here's the point B. And we're trying to figure out the coordinates of that point B, and that'll give us the vector from A to B. Well, what do we know? We know that this angle is 30 degrees. And then, if you remember your SAT study book, this angle then has to be 30 degrees. And so now you could do the, do it in terms of trigonometry and do the coordinate, the signs of the components yourself. I tend to just say, like, I just tend to do everything counterclockwise from the positive x-axis. So here, this would be, to get from here to the vector, you'd go 180, backtrack 30, so 150. Plug it in your calculator, cosine and sine of 150. So the vector we want is 0.5 times cosine of 150, 0.5 times sine of 150. And that is negative 0.433, right? And then 0.25. Any questions about that? Okay, so let's do another example. That was an example where it made more sense to use that sort of second way of thinking about it. We didn't already have the coordinates. So in the second example, let's say what's a vector from the point 10, 2 to the point negative 4, 6. In that case, we already have the coordinates, So we'll use the first approach. So the vector we want is just the destination, -4, 6, minus the starting point, 10, 2. And so you get -14, +4. Any questions about that? Another thing that's going to be really important to us is calculating a unit vector in a given direction. The reason that this is going to be important is because figuring out a unit vector lets you, a vector has two properties. Magnitude and direction. And calculating a unit vector lets you separate the vector into those two properties. You can think of that unit vector as being like a pure direction. So think of that as like the pure direction. And so if you have a vector u, you can think of that as equal to this scalar that represents the magnitude times a unit vector in that direction. That's what that fancy hat means. And then we'll see that there are a lot of problems where you either know the direction but don't know the magnitude, or you know the magnitude but you don't know the direction. And this lets you take, okay, so in 2D, most of our problems are going to be in 2D. How many unknowns are there if you don't know anything about a vector? 2, right, the two components. In 3D, there's 3 unknowns. But if you can represent a vector like this, and you know either this one or this one, even though you don't know what that vector is, you can cut the number of unknowns down to a single one. You can think of it as a unit vector represented by an angle theta, or you can think of it as a magnitude, like a scalar value. And so since all of our problems are going to be attempts to get a number of equations to catch up to a number of variables we're trying to solve for, if you can cut down on the number of variables with something like that, it's going to be important. Okay, so there's 2 ways to calculate a unit vector. The first one is if you're given an angle between the vector and some reference line. I guess it would have to be a reference vector. This is only useful in 2D. I would never use this in 3D. It just gets more complicated than is necessary. So think of that as 2D only. And even in 2D, a lot of times it's useful to use the other approach. So let's say, and not always in 2D. And then the second one is given the endpoints of a vector in the same direction. This one will be sometimes useful in 2D. And I would just always use this in 3D. Okay, so the first one, given an angle from a reference vector, so for example, let's say that you have that your vector makes an angle. So there's your coordinate system, x and y axes. And let's say we know that there's an angle of 20 degrees between basically the negative y-axis and the vector that we want to represent. So this is the vector we want to represent as a unit vector in that direction. So we want to find a counterclockwise angle. CCW is counterclockwise from the positive x-axis through the vector. And then once you know that, the unit vector is just equal to cosine theta. Find the counterclockwise. So this angle theta is that counterclockwise angle. The unit vector is cosine theta, theta, sine theta. So in this example, I'll just continue the, show the negative x-axis. So starting at the positive x-axis, to get down to this green line, that reference line, would be 90, 180, 270. But we didn't quite go that far, so backtrack 20, so theta is 250. And so the unit vector here is cosine of 250 sine of 250. You could also, make that triangle, and that's in the third quadrant, and think of it that way. And then, the components are both negative, so I think that would be 0.1. 20. Yes. Yes. I think I'm planning to talk a little more about that. But, yeah, so we know that the reference line is this, right? It's 20 degrees from that. And so the angle that you want is always the counterclockwise angle starting at the positive x-axis. So if you know the angle from, so our reference line is this, you know? So figure out how far you have to go counterclockwise from the positive x-axis to get to the reference line, and then go clockwise or counterclockwise from there to get, so it would be 270 to get to the solid green line, minus 20. Yep. And instead of going counterclockwise, you could also go, call it a negative angle and go clockwise. So you could also go negative 90 minus another 20, so negative 110. Okay. And so this would give you negative 0.342, negative 0.94. And actually, that way of thinking about those angles is going to be a really useful thing in this class. And I wanted to do one example. So let's say we haven't talked about joint types or anything yet, obviously, but one type of joint that we'll see a lot is one where two objects are connected by a pin that can slide freely in a slot with a certain, it can move in one direction. So imagine these two objects are connected. So let me just sort of describe what's going on here. So these are like two bars. And the idea is this is a pin that's part of the bar in the background. Okay. And this bar can rotate around that pin or slide along that slot, but it can't slide in any other direction. Okay. When we talk about joints, I'll bring in examples and stuff. So let's say that this angle is 50 degrees with the horizontal. And if we're drawing a free body diagram of one of these two bars, this is not anything you have to know yet. Okay, but I'm going to tell you. So if we're going to draw a free body diagram of either of these two bars, the direction of the force that's applied by one to the other at this joint has to be perpendicular to that pin. And it sort of makes sense if you think about the fact that, like, how much force would that joint apply to these two bodies if you just very carefully, like the game operation, just like moved it along the slot without ever letting the two touch each other? What force would that apply? None. They're not even touching, you know? The only way they can apply force is if you try to move one perpendicular to that slot. Okay, so now if I'm going to draw a free body diagram of this part of the background piece. I'll call this one body 1 and this one body 2. So here's a free body diagram of this part of body 1. Well, the direction of that force is perpendicular to that slot. Okay, that's a 90-degree angle. We don't know what the magnitude is, so I'll just call it F. So this is one of those cases where we don't know what that force vector is, right? So at first thought, you might think, okay, that's two unknowns, an x and a y component of a force vector. But if we take advantage of the fact that we know the direction, okay, and we represent this direction as a unit vector, then we're down to only one unknown because we just have this scalar f multiplied by a unit vector that we can know, okay? So that's the benefit of using unit vectors. Okay, so what we have to do, though, in order to get that is we have to know, we have to be able to represent this unit vector in components in our coordinate system. And let's say we're using like a standard coordinate system. Oops. Okay, so how would we do that? Well, the way that I like to think about doing that, this is going to be a really useful thing in this class, is just start at the positive x-axis of your coordinate system, and then just bop around finding things finding angles that you do know, from one reference to the next reference, to the next reference, to the next reference, going positive if you're going counterclockwise, negative if you're going clockwise, until you come up with the vector you want. So I'm going to start in the order, and the location doesn't matter. We're just talking about the orientations. So the first thing we know is that if I start in the positive x-axis, it's 50 degrees to get into this orientation, right? And the next thing we know is once we're at positive 50 for our angle, it's 90 more degrees counterclockwise to get this vector, right? So 50 plus 90, and so the angle from the x-axis to this F is positive 140 degrees. So let me write it like this. There's the coordinate system. Here's the first vector we know. Here's the second vector we know. And so theta, this is the unit vector we want. So theta is equal to positive 50 plus 90, so 140 degrees. And so the unit vector is just cosine of 140, sine of 140. And that is negative 0.766, positive 0.643. And now the benefit of that is, this is what I was saying before, but before we did the unit vector thing, if we wanted to represent that unknown vector, we'd have an x component and a y component that we don't know. So that's two unknowns. Now this vector that we want is just some scalar. Well, let's write it. So it's just some scalar f times a unit vector, or in other words, negative 0.766 f, positive 0.643 f. And we've reduced it from two unknowns to one unknown. Yes! That's the kind of enthusiasm I expect to see. Okay. So that is the approach where you know the angle from some reference vector to the vector that you want. The other thing that we're going to have to do pretty often is figure out a unit vector that's in the direction of another vector where we know the two endpoints. Can you think of a case where that would be, that's probably not a fair question. Okay, here's the case where that's going to come up most often in this class. If you're trying to figure out the force that's applied to an object by a cable, okay, the cable force is always parallel to the cable itself. The cable itself has a point here and a point here. you know? And so you can figure out the direction of a vector going from the body to the other end of the cable, and then normalize that, come up with a unit vector in that direction, and that'll, and then you can do the same thing we're doing here, represent that force vector as a scalar times a unit vector. Okay. So the second approach is a unit vector in the direction of a vector from point A to point B. Well, we know that a vector going from the point A to the point B is B minus A. The magnitude of that vector U is, we can get that as the square root of the sum of the squares. And then the unit vector is 1 over the magnitude times the vector. So figure out the length and divide both components by the length. Let me do an example. It works the same in 3D. So the only difference is this vector U magnitude is just the x component squared plus the y component squared plus the z component squared, all square root. Everything else there works in 3D. Okay, so here's an example. So let's say we have a beam connected to the wall, this time by a pin joint like a hinge. Well, if that's a frictionless hinge, then if you didn't attach this to anything else, it would just swing down to the wall. So let's say that it's supported by a cable like this. And we don't know what the angle of that cable is, but we do know that the endpoint here is at coordinates 4.52, and the endpoint here is at coordinates 2.51. A free body diagram, I'm only going to draw the end with the cable, but what's the direction that that cable force would apply to the beam? It's parallel to that cable. Which way is it? Toward the body or away from the body? Away. Yep, it's pulling on it. So we know we have a force vector like that. We'll call the magnitude T. But again, we have that same situation where if we didn't use the unit vector thing, that force vector would be represented by two unknown components. if we take advantage of what we know about those coordinates and represent it as a scalar times a known unit vector, then we've cut it down to one unknown, which means we have one less equation to find. Okay, so we want a unit vector in that direction. In other words, we want a unit vector in the direction that goes to this point from this point. Okay. So the non-unit vector is 4.52 minus 2.51, and that's equal to 2, 1. What would happen if we would have said that this force vector was pointing toward the beam instead of away from the beam? Yeah, we would have started by saying this minus this, and we would have gotten -2, -1, and everything just would have been backwards. So don't do that. The magnitude of this vector is 2 squared plus 1 squared square root. So root 5. And so the unit vector is 1 over square root of 5 times the vector 2, 1, which is 2 over root 5, 1 over root 5. And now that force vector that otherwise would have been 2 unknowns is equal to the scalar t times this unit vector, or 2t over root 5, t over root 5. Any questions about that? Okay, here's an example problem I'd like you to think about for a second. You can talk to each other about it, ask me questions if there's anything that you're not getting or whatever. But this is just sort of to help you wrap your head around this while I'm here to answer questions. Okay, so let's say that we have a wall that makes a 60-degree angle with the horizontal. And a force vector, F, that makes a 15-degree angle with the wall. What are the components of the force vector using just one single unknown, only one variable? And let's just use a standard coordinate system like this. Okay, take a few minutes and see if you can think through that, talk through it, show each other your answers. If somebody's answer doesn't make sense, make one of those faces. Yep. Oh, yeah. Everybody, yeah, do this stuff. It helps. Okay, so I'm going to start by I'm going to draw the coordinate system with all the positive and negative axes. And I'm going to do this by drawing just a bunch of vectors. All their tails have to start at the origin. So first of all, we know that it's 60 degrees from the x-axis to here, right? We know this is 60. But it's not 15 degrees from this one to this one. It's 15 degrees from the opposite of this one to this one. You see that? You can only use angles between vectors that have the same tail. Think about that. I think that'll sort of make sense if you think about it a little. And so, okay, so we have this one 60. The opposite of that is, this angle's 180. Now the angle between this one and the one we want is 15. This 180 goes all the way to the second one. Okay, so the angle is, we'll just start adding these up now. Theta is equal to plus 60 plus 180 minus 15. So that's 240, 225. And so this unit vector is cosine and sine of 225. Which is, I think that's 45 degrees from, that's like 45 degrees from either of these two. So that is negative 0.7071, negative 0.7071. Let's see. Now that's the unit vector. Then the force vector is magnitude of that force, F, times that unit vector. So you get negative 0.7071 F, negative 0.7071 F. That's the first of 1,000 times you'll have to do something like that. And, if it doesn't make sense yet, it'll make sense once you do a bunch of them. But does anyone have any questions about that? Okay, well, stop there. So for Tuesday, I'm going to assign all of the vector problems that are given. And you're not going to turn them in. You're just going to 3-hole punch them or whatever and put them in your binders under the assignments. Okay? Have a nice weekend. Yep.
On that, do you want us to print out the actual assignment, punch it, and put that before our work?
Yes, I think that's the best way to do it.